Hello everyone, and welcome to today's chem lesson. Today we are going to spend some time talking about the radius of an atom, how far out the electrons can get from the nucleus in their shells. This is going to be the last of our three trends that we look at, having already looked at ionization energy and electronegativity. Atomic radius is going to be another thing that we can look at placement on the periodic table to tell which atom is bigger or smaller. Now, we've been looking at a shell model of the atom, which has our positive nucleus in the middle and the electron shells around the outside. And we keep drawing it this way, but we have to remember that these little arcs that we put here represent fully circular shells, right, that go all the way around the atom. I'm not great at drawing circles, but this is the idea that we're looking at. We know that each shell is bigger than the one that came before it because they are concentric circles, right? Smallest and bigger and bigger and bigger and bigger. We also know that in the nucleus we have our positive protons, our neutral neutrons, and out here in the shells is where our negative electrons are. And the thing holding the electrons here in the shells is the pull of the nucleus. The electrons are moving really quickly around the nucleus and being held in their shells by the positive pull of the nucleus. And when we look at the radius of an atom, and we want to tell which atom is bigger than another atom, the number of shells that that atom has is going to be pretty important. Because obviously something with 4 shells is going to be bigger than something with 1 shell. Because the fact that there is 4 shells here automatically makes it bigger than something with 3 or 2 or 1. And we're going to look at our 4 corners again. And we're going to try our best to identify which is the biggest of the 4, which is the smallest of the 4. Before we do that, there is an important little note down here at the bottom. The nuclear charge, which is a phrase that we will see sometimes on questions. Nuclear charge refers to the number of protons in the nucleus. Because if we're talking about nuclear, I'm talking about the nucleus, and then the charge, we have protons in here and neutrons in here. Neutrons have no charge, so they are not going to be contributing to something called nuclear charge. So all we're left with is how many protons there are. All right, it's always going to be positive, and it's always going to tell you how many protons there are. Now, let's take a look at these 4 corners. We're going to take the same atoms. We've got lithium in the upper left, fluorine in the upper right, francium in the bottom left, and unseptium in the bottom right. Lithium and fluorine have 2 shells. Francium and unseptium have 7 shells. Lithium and francium have 1 valence electron. Fluorine and unseptium have 7 valence electrons. And right away, thinking about these shells and how they are concentric circles, we can immediately tell which two atoms are bigger here. The two bigger atoms are going to be francium and ununceptium. They're going to have 7 shells, which is going to put them way above lithium and fluorine. And so for the first time, this trend actually points downwards. Telling us that as we go down row by row, the atomic radius is going to increase. And our reasoning here is because more shells are bigger than fewer shells. So if we pick any column and we look at it from top to bottom, we know that it gets bigger as we go down one element at a time. But when we look at francium and ununceptium, we're looking at two things that have 7 shells. How would we know which one of those two things is bigger than the other? When we look at lithium and fluorine, we're looking at two things that have 2 shells. How would we know which one of those is bigger than the other? And what we've used previously in all of our other trends, what we've looked at is the number of valence electrons. That has been our deciding factor when we look left to right along the table. For ionization energy, the more valence electrons there are, the harder it is to take the electron away, the higher the ionization energy. For electronegativity, the more valence electrons there are, the more the atom will pull in on those new electrons. But here in this case, we're actually not using valence electrons in order to help us out. We are using nuclear charge. Right? Very correctly and very astutely pointed out in the chat there. We are going to look at the nuclear charge of each of these things in order to help us determine which of these, right, either lithium or francium, or sorry, lithium or fluorine, or francium or ununceptium, which one of the two is the bigger or smaller. Because at the end of the day, 7 electrons in 2 shells is just about as big as 1 electron in the second shell. Right? The shells are very static, right? They can move a little bit, but the number of electrons in them is not going to be the thing that makes them expand or contract. The thing that makes them expand or contract is actually going to be the nuclear charge. How strongly is the nucleus pulling inward on those shells? And so what we end up looking at is lithium with 3 protons pulling in on 2 shells. Versus fluorine with 9 protons pulling on 2 shells. Because 9 protons pulling inward is going to be stronger, right? If you've got 9 people pulling on something versus 2 people pulling on that same thing, the 9 people are going to do a better job. They're going to be stronger in total than 2 people are. So 9 protons pulling inward on 2 shells is going to actually contract those shells. It's going to pull them in closer to the nucleus, which actually is going to make fluorine smaller and lithium a little bit bigger. Those 9 protons can take that second shell and pull it just a little bit inward to make fluorine smaller than lithium. And the same logic is actually going to apply down here to francium and unseptium. 117 protons pulling on 7 shells versus 89 protons pulling on 7 shells. The 117 is going to be able to pull those 7 shells inward, right? Shrink the whole thing down just a little bit, make it a little bit more compact, making unseptium smaller than francium. Which means that our trend here is actually going to go from right to left. I'm not able to draw out all this morning. As we go from right to left, atomic radius is going to increase. And the reasoning is because a smaller nuclear charge means a weaker inward pull on the shells. So lithium with its nuclear charge of +3 versus fluorine with its nuclear charge of +9 means that fluorine is going to be smaller. It has a better inward pull. It's better able to contract itself inward and kind of shrink itself down versus lithium, which pulls, right? Pulls inward on those 2 shells, but not as strongly as fluorine does. And again, that same logic applies down here to francium and unseptium, where unseptium is just a little bit smaller than francium is. If I were to give you 4 atomic radii, would you be able to correctly assign them to their atoms? If I said one of them was 80, one of them was 90, one of them was 170, and the other was 180. Can you correctly assign these 4 atomic radiuses to these 4 elements? when we look at these four elements, we know that the two biggest elements are going to be the ones with the most shells. We know that the atomic radius is going to increase going down the columns. So we know that the 170 and the 180 are going to be applied down here to francium and ununceptium. Of those two, we know that francium is the bigger one, right, using this nuclear charge piece. So we know that the 180 is going to be applied to the francium, and the 170 is going to be applied to the ununceptium. We know the two smaller elements, the two smaller radiuses, are going to be these ones up top, the ones with two shells. That same atomic radius increasing from right to left, that same nuclear charge pattern that we're going to talk about, or that we talked about, is going to tell you that lithium is the 90 and fluorine is the 80. The smallest atoms are going to be in the upper right, and the biggest atoms are going to be on the bottom left. Right here, the row is more important than which column it's in, right? Left to right is a weaker trend, right? This is only a difference of 10, but here we have a difference of 80, 90. Each shell adds more to the radius because each shell is bigger than the one that comes before it. So 3 shells is always bigger than 2 shells. 4 shells is always bigger than 3 shells. But this isn't all we're here to talk about today. Today we also want to mention and talk about the radius of an ion, which is going to be slightly different than these radiuses here. These are all atoms. They have neutral charges. They have the same number of protons as electrons. But what happens when these things become ions? How does that change the radius? When I look at something like lithium or francium, lithium and francium both have one valence electron in their shells. Right, lithium has 2 shells. Francium, which I'm not going to draw here, is the one with 7 shells and 1 valence electron. Florine and ununceptium are the ones with 7 valence electrons. When we look at these two elements, we know, because we've talked about ions and what makes an atom stable, we know that these two things are not stable. They would like to become stable. They want to look like a noble gas. They want to fill their valence shell. They want to empty their valence shell. How is lithium going to become stable? What is lithium going to do? Lithium with 1 valence electron. What is lithium going to do to become stable? remember that elements are always going to take whichever is the smaller number. So it could take 7 electrons, gain 7 electrons, or lose 1 electron. 1 is smaller than 7, and so lithium is going to lose 1 electron to become an ion. To become lithium plus 1 with 2 electrons in its first shell and now an empty second shell. What happened to the radius of lithium when it became an ion? How did this radius change? Lithium lost an entire shell. Right? This isn't here, it's an empty shell. So lithium got smaller by becoming an ion. Let's pause that there and take a look at fluorine. What does fluorine want to do to become stable? Fluorine, with its 7 valence electrons so close to a full shell of 8, was really going to want to gain an electron. And so, when we look at fluorine, it will get its 8th valence electron here. Now, it still has the same number of protons. It still has the same number of shells, but it has gained 1 electron. What do you think that will do to the radius? Do you think the radius is going to get smaller, bigger, or stay exactly the same? All right, remember, these I'm not a computer that can draw things to scale or even make good-looking circles. All right, good. It is going to get the tiniest bit bigger because it does have that 1 extra electron to hold on to. And so we see one more little pattern here. And that pattern has to do with the charge and comparing that to the ion. When an atom becomes a positive ion, when an atom loses electrons, it becomes smaller. Sometimes it loses a whole shell. Other times, it just has fewer electrons to hold on to, meaning it can pull a little bit more strongly inward on those shells. A positive ion is smaller than its atom. Right, this positive lithium ion is smaller than this neutral lithium atom. And the opposite is true of negative ions. This negative fluorine ion is bigger, ever so slightly, but still bigger than its neutral atom counterpart. And so, in order of importance for size, radius, the most important thing, the thing that automatically determines if something is bigger or smaller than something else, is the number of shells. Right? More shells means bigger. Automatically. No matter how many neutrons, how many protons, how many electrons, none of that matters. If something has more shells than something else, it is bigger. If we're looking, then, at two things that have the same number of shells, if we're looking at lithium and fluorine, which both have two shells, the second thing that determines which one is going to be bigger is going to end up being the nuclear charge. A smaller nuclear charge is a bigger atom. So lithium with only 3 protons is bigger than fluorine with its 9 protons. And the least important factor for looking at the radius of something is going to be the number of electrons. If you have two things with the same number of shells, the same nuclear charge, the only thing that's left to break the tie is the number of electrons. And in that case, more electrons is going to be a bigger ion, or a bigger atom. And as we look down this ranking, the shells are going to have the biggest effect, right? Gaining a shell or losing a shell is huge. Looking at the nuclear charge, if the same number of shells, the nuclear charge is going to make a very slight difference. And then if they have the same shells and the same nuclear charge, we're going to have something that is even a slighter difference than before. Right, on the previous slide, when we assigned atomic radiuses, we said lithium was 90 and fluorine was 80. Right, this difference in nuclear charge accounts for a change of 10. If we're looking then at comparing fluorine and a fluoride ion, this change is going to be even more slight. We're not even looking at a change in 10. We're looking at a single-digit change in radius. So this is the biggest effect, the number of shells. A smaller effect and an even smaller effect. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.